In today's lecture, we will see a very important formula which finds its application in almost all theories of all chapters of statistical mechanics. When we will study the different theories of statistical mechanics in its different chapter, certainly you will find the application of this very important formula, which is called Stirling formula. People also say this formula as Stirling theorem. So this is just a basic fundamental. You have to remember this formula, but in this lecture our aim is to know what is this formula and how we can derive it. Although its derivation is not very important, but this result should be always in your on your fingertip or in your mind, because it will be used variously in different theories. Okay. So first of all, I would like to say a few words regarding this formula, that why we need a Stirling formula. As you know, if n is, let us consider a number, n is a number, then you know that n factorial is equal to what? This is equal to n times n minus 1 times n minus 2 times so on times 3 into 2 into 1. Okay, you know. You can think, if n is actually a very large number, if you consider n is very large, as in statistical mechanics, we always talk about a system consisting of a large number of particles. So definitely we will be encountered in theories very large number. So if n is very large, then you can see that the calculation of this n factorial will be troublesome. Okay. So to overcome this problem of evaluation of this n factorial, Stirling devised a important suitable analytical approximation of ln n factorial. And what will be ln n factorial when n is very large? Remember, this formula which we are going to discuss will be valid only when you talk about a very large value of n. So as I have told you that the evaluation of n factorial becomes difficult, it is very troublesome when n is very large. So to overcome this difficulty, this trouble, Stirling's formula gives a suitable analytical approximation of ln n factorial for large values of n. Okay. So first of all, we should know what is this Stirling formula, and then we will see its proof. Although proof is very simple, and as I have told you that the proof is not very important, but to memorize this formula for its use in different theories is most important. So this formula actually says that if n is a very large number, then ln n factorial, that is log n factorial, will be equal to n log n minus n. I have written it here. Okay, this formula is actually called a Stirling formula, or you can also say that this is a Stirling theorem. Now we will see how we can prove that this log n factorial is equal to n log n minus n. How we can prove it? So let us see its proof or its deduction. You can say either deduction or you can say its proof. How we can prove this result? Okay. As I have told you, you know that n factorial is equal to what? This is n times n minus 1 times n minus 2 so on times 4 into 3 into 2 into 1. Okay. Now as in a Stirling formula we have to evaluate log n factorial. So let us find this log n factorial. What will be this log n factorial? You can see. Since n factorial is equal to n into n minus 1 into n minus 2 into so on into 4 into 3 into 2 into 1. So when you will take its logarithmic value, that is log n factorial, you know that log a into b is equal to log a plus log b. So from that formula we can write that this will be equal to log n plus log n minus 1 plus log n minus 2 so on plus log 4 plus log 3 plus log 2 plus log 1. Okay, this is very simple concept. But as you know that log 1 is equal to 0. So the last term will be 0 and so our result is what? This will be log n plus log n minus 1 plus log n minus 2 so on plus log 4 plus log 3 plus log 2. And this series can be written in more compact form by the use of sign of summation. So you can equivalently write that ln n factorial is equal to summation x 2 to n log x. Okay. When you will substitute the value of these limits of for x, that is 2, 3, 4 up to n, then you will get this series. So this expression can be written as log n factorial equal to summation over x from 2 to n log x. Okay. Now actually we will plot this log of x in against of x. Okay. We will plot a graph of ln x in against of x. What will be that graph and what information from that graph will actually we will obtain, we will now see. See here, I have actually plotted this ln x in against of x for the values of x from 2 to n at a step of 1. It means you have to take the value of x as x equal to 2, then you have to take x equal to 3, then 4, and in this way you have to take x equal to n. Okay, so this full line curve, you can see it here. This is actually the graphical plot, or this is the curve obtained when we actually plot this ln x in against of x at a step of 1 starting from x equal to 2. Okay, so you can see when x is equal to 0, ln x will be ln 1, which is 0. So here when x is 1, this curve actually touches the x-axis, you can see. And when x is equal to 2, then ln x will be log 2. So this is the value of log 2 at this point. Log x will be log 2. And similarly, when x is 3, then the value of log x will be log 3. So this point actually represents log 3. I have marked it here. In this way, you can see that at a step of 1, we have actually taken the value of x and this curve is obtained. Okay. Now, you can see this dotted lines. Actually, if you want to find the area under this stepped curve, a stepped curve means you have to find the area under this curve which I am just marking here. Okay, and then you have to find the area under this curve. These are actually the stepped curve. Okay, so what will be that area? You can easily think. Let us see. If I am marking it like point A and like point B. So area of AB21 will be what? This length of this side of this rectangle is equal to log 2. Okay, and this length is 2 minus 1, that is 1. So area of AB21 is equal to log 2 into 1. And similarly you mark it by C and it by D. So what will be the area of the rectangle CD32? That will be actually equal to log this side, that is C2 side, is equal to log 3, and this CD or this 2 3 is again equal to 1. So that will be log 3 times 1. Okay, so in this way, if you want to find the area under the stepped curve, what will be the total area? The total area A will be equal to log 2 times 1 plus log 3 times 1 plus so on in this way, and finally we will get actually log n times 1. Okay, and so this can be written by the sign of summation like this. This is simply ln x, where x runs from 2 to n. 2 to n. Okay, I have actually written it here. You can see that the area under the stepped curve is equal to what? If you write this area by the symbol A, this will be log 2 times 1 plus log 3 times 1 plus so on plus log n, yes, log n, not here I have written, yes, this is log n, and log n times 1. Okay, and in brief we can write it summation log x, where x runs from 2 to n at a step of 1. Okay, but you have seen earlier that this expression, that is summation log x from x equal to 2 to n, this is equal to log n factorial. So there we can put, instead of this summation log x 2 to n, we can write log n factorial. So you can see I have written here that this is equal to log n factorial. Okay, now you can see when we consider actually the large values of x, see here you can see that this is the full line curve, that which represents actually log x, and the stepped curve, although I have overwritten here, so this actually appears like a full line curve, but as you have marked here, as you can see here, sorry, the page has been turned, but this will be okay. So let us see, this will be just okay. So see here, this stepped curve and the full line curve, see here, when x lies between 1 and 2, then this stepped curve and this full line curve are actually very distinct, very different. Okay, even when x lies between 2 and 3, then this stepped curve CD and this full line curve BD is very different. But now see, when the x lies between 6 and 7, that is, we take the larger value of x, then you can see the stepped curve and this full line curve, these are not very distinct, but almost the stepped curve overlaps with the full line curve. Okay, so from this we can conclude that for the large values of x, the stepped curve and the smooth curve or the full line curve of log x become indistinguishable. Okay, and so we can approximate this ln n factorial. You can approximate this ln n factorial by integration of ln x instead of summation, because you know in case of continuous function the summation becomes integration. So you can see actually here this log n factorial is equal to summation over x 2 to n ln x. But if we consider that n is very large, in that condition the function becomes continuous, because the stepped curve and the full line curve or the continuous curve that is actually not different. And so this summation will become integration. We will then integrate this ln x with respect to x from x equal to 1 to n. Okay, and that's why we simply say that this approximation is quite satisfactory for large values of n. I have written it here. You can say that this approximation is quite satisfactory for large values of n, since this log x in the range of large values of x varies only slightly when x is increased by unity. Okay, and so if you are considering the large values of x, then we should simply replace this summation by integration. Okay, so what will be now this ln n factorial? That will be integral of log x with respect to x from x 1 to n. Okay, so you can see I have written it here that ln n factorial is equal to integral 1 to n log x dx. Actually I have multiplied this log x by 1 because this multiplication makes no difference. Now to evaluate this integral, you have to actually follow the rules of integration by parts. So for following the rules of integration by parts, I have multiplied this log x by 1. So here there are two factors. First one is log x and the another is 1. Okay. Now as you have to follow the rules of integration by parts, so you must remember the technique of eyelet. You know, in this word eyelet, which later comes before, that is taken as a first function. So I stands here for inverse, L for logarithm, A for algebraic function, T for trigonometric function, and E for exponential. Here actually this ln x, this is actually logarithmic function L, and 1, this is algebraic function, that is A, and L comes before A. So for following the rules of integration by parts, we should take ln x as the first function and 1 as the second function. Okay, have you understand? Ln x will be taken as the first function and 1 will be taken as the second function. And you have definitely the formula of integration by parts in your mind. You know the formula says first function. So first function is ln x and integral of second function. So what will be the integral of 1? Integral of 1 dx will be simply equal to x. So here I have written x. So first function into integral of second function, and limits are what? Limits are 1 and n. Okay, minus, then in formula there is minus integral of differential of first function. You know that differential of first function, which is ln x, that is equal to 1 over x. So differential of first function, I have written here 1 over x times integral of second function. Again, integral of second function will be equal to x. So here there is x. Okay. And limits are 1 to n. Now let us put the limit. When you will put the limit in first term, there will be what? At the place of x, we will now write n. So this will be n into log n and minus now 1 into log 1. 1 into log 1. But you know log 1 is equal to 0. So here this second term is 0. And minus. Now here this x and x will cancel out. And you have to integrate only dx. And the integral of dx will be x. So this is x and limits are 1 and n. Okay. Now this will be n log n minus. Now put the limit. This will be n minus 1. Okay. And that will be n log n minus n plus 1. But as our assumption is what? Our assumption is n is a very large number. When you say n is a very large number, it means n is much greater than 1. So if n is much greater than 1, we can neglect this 1 in comparison to this n. So 1 has been neglected here. And after neglecting 1, what will be our result? You can see this is log n factorial equal to n log n minus n. And you can see this is nothing. This is simply the Stirling formula. So you have seen how easily we can obtain this Stirling formula or prove this Stirling theorem. So this is a Stirling formula. And as I have told you that this formula is very important. It finds its application almost in all concepts of all chapters of classical mechanics. Of statistical mechanics. Okay. And therefore, definitely this formula should be always in your mind. Okay. In statistical mechanics, the condition that n is very large will always met, and therefore this formula is always used in statistical mechanics. So this is a very important formula, and this was actually a very short lecture of today because this is just a basic fundamental, but as it will be used various times, and definitely in your mind there is a question how this formula actually why we write like this, how this formula can be proved. So I have actually discussed this formula, but again I will suggest you must remember this formula for its application. Okay. So thank you very much.